about NMOS current mirrored MOSFETs. Now we have this PMOS configuration, PMOS transistors, which are in supposedly current mirror configuration. But the currents you see over here, for example, in this example, this IRF2 and IQ2 are different. Okay, I mean the idea is that even if these transistors are in saturation, in which case if you recall previously, okay, here we have this M3 and M2, which are NMOS, and they're used to provide a constant current bias to the transistor M1. So in order to stabilize the Q point, okay, that's the story. So this IREF, which is the drain current, which is also the drain current, ID3, was we set this to be equal to ID1, okay. And the reason was, and this ID1 is the same as IQ1. You see over here, this ID1 is the same as IQ1. Now, the reason was that you see that VGS over here, VS3, VGS2 are equal. So you recall that the drain current in this saturation region, if you have the same conduction parameter of the transistor, let's say capital Kn for NMOS devices over here, multiplied by VGS minus, this is VGS, minus the threshold voltage, and if the MOSFETs are the same, they have the same threshold voltages, VTN. I mean, for these M3 and M2 MOSFETs, if they have the same threshold voltages, okay, the VGS is the same since they're connected in parallel. The gate is tied together, and the source are connected together over here. The VGS is the same, conduction parameter is the same. So that means these are just like they both have the same drain to source current. So those are called current mirror MOSFETs. Okay. Here, in this example, let's read this out. It says design the circuit shown in figure 49b. So this is 49b over here, and you are required to provide a bias current IQ2 of 150 microamps. So IQ2 over here is supposed to be 150 microamps. So the other thing is, in order to have, as we have talked before, in order to have the same IRF2, we need the same conduction parameter, same gate source voltages, same threshold voltages. So over here, let's see, we have the same. You can see that VSGC, the source are tied up together, the gates are connected together of transistors MC and MV. So VSGC is equal to VSGB. Okay, so the idea is that you see this is a PMOS device, and you need a negative, you need to apply a negative gate voltage in order to create an inversion layer. I mean, the threshold voltage is already less than 0. Okay, so the threshold VTP is less than 0. That is expected. So the source is at higher potential. So you write it as such. Okay. So anyways, okay. So VTP is a negative for all transistors because all transistors are PMOS. The channel width modulation is 0, so you can consider all of the PMOS devices to be ideal. I mean, you don't need to consider the forward resistance R not in the saturation region. Okay, so these are ideal transistors. Similarly, your process conduction parameter, which consists of the product of the channel oxide, not the channel oxide, the silicon oxide beneath the gate, and per unit area multiplied by the mobility of the positive pole carrier is the same for all transistors. Okay, so this is also the same for all the transistors. But the width to length geometrical ratio of the channel is different for the transistor MC and transistor MA. So if you have, I mean, you see this IRF2 is also different. So this, even if for the same VSG and same VSGB, the current which is given as for PMOS device, this is given as KP. Okay, then you have your VSGC, so VSG plus VTP, which is negative VTP whole squared. Even if VTP is the same, VSG is the same. Due to different KP, you have different different IDs. Okay, this ID is not going to be the same. This ID is going to be different for MC and MB. Okay, because the geometrical parameters are different. You will find out that this W by L for the transistor MC and MB are different. That's the reason why you have, even if for same for a constant current biasing, you have different reference and IQ2 currents. Okay, so what it says is, since the bias current IQ2 and the reference current are not equal, the ratios WL of the current mirror transistors MC and MB will not be the same. Okay, so that is expected. So let's start the DC analysis. You see, you take this. This is not IDC. This is for the transistor MC over here. This is basically the direction is as such as inside the source, out of the drain. So over here, the drain current is IDC, which is in fact equal to your IR2. Okay. Then similarly, you have this current IDA, well, IDA, and then this current is also the same as okay, IQ2, which is nothing but IDB. It's all these are all the same things. Okay, but these two current, this current and this current is not going to be the same, although all the transistors in saturation region. So for MC, if you write the expression IV characteristic for the saturation region, you see that WL is given. Okay, this is 50 for transistor C. Kp is 40 for all the transistors. Kp is 40. This is given over here, 40. Okay. VTP is the same, minus 0.6, and then you plug these values for 250 microamps. That's the drain current for the transistor MC, to find what VSGC is, and this turns out to be 1.513 volts. Okay. Then okay, then you see that since VSGC and VSGB are the same, so for the transistor MB you can find IQ2. Sorry, you don't find IQ2. IQ2 is given. I mean, for the same for the required IQ2, you find out what the ratio WL is. I mean, since it's not at 250. If it was 250, you see this parameter is the same. This parameter is the same. WL by the same. Then it was supposed to be 250, but due to the different conduction parameter, due to the different geometrical size or the width and the length ratio of the channel, since the channel dimensions are different, which is 9 in this case for transistor MB, for MB WL, the ratio is the same, is different as compared to what you have over here, MC. So MC was equal to 15 over here. Okay, and this is equal to 9. So this causes the difference in the current IDB and IDC. Okay, so let's find out for the transistor MA, again for saturation. IDA over here is given as Kp by 2. So this is the conduction parameter. VSGA, VTP is the same, minus 0.6. WL by is given in the statement of the example. WL for transistor A is 25. So let's plug this in over here. This is 25. Kp is again 40. IDA is same as IQ2. So you find WSGA is 1.148 volts. Okay, and you see that okay, now for the source to drain voltage, you apply the KVL on the output loop. Okay, since IQ2 is the same current as your IDA. Okay, IDA, so there will be a drop across the load resistor RD. So you can find your VSGA as VSGA minus the drop at the load resistor. Okay, then negative of the supply at the which is connected to the drain of the transistor MA. So this comes out to be 2.95 volts. Okay, now if you want to check that if the transistor MA is indeed in the saturation region, you can find this by the overdrive voltage. VSG plus VTP is going to give you your drain to source, sorry, VSD sat. Okay, this is VSD sat. So let's find out what this point is. So let's write this VSD sat. So this point is equal to, and for transistor A, VSGA, what is VSGA? We just found it out. So 1.148 minus 0.6 minus for all transistors, VTP is 0.6. So, but VSD is greater than whatever this comes out. This is it's even less than 1. So this is, you see, sorry, this 2.95 volts is greater than this value. 2.95 volts is greater than this. This means that you are indeed in the saturation region. I mean, you are You are in the saturation region. This point is somewhere at the knee of the curve, and your Q point lies somewhere above this. Okay, you are above this point. 2.95 volts is greater than 1.4148 minus zero point 0.6. So you are indeed in the saturation region. MA transistor is operating in the saturation region. Okay. So you see that by designing different ratios of the current mirror transistors, we can obtain different reference current and the bias current values.